Hello everyone. Today we'll discuss few page replacement algorithms. First we'll see what is this page replacement algorithm. So in an OS that uses paging as memory management scheme, then a page replacement algorithm is needed to decide which page needs to be replaced when new page comes in. And now what is page fault? This page fault happens when a running program accesses a memory page that is mapped into the virtual address space but not loaded into the physical memory. Since actual physical memory is much smaller than the virtual memory, page fault happens. So in case of page fault, OS might have to replace one of the existing pages with a newly needed page. Okay, and few of the page replacement algorithms that we are going to discuss are FIFO and least recently used. FIFO stands for first in first out, and LRU, that is least recently used algorithm. Now we'll see one by one. The first one is FIFO, that is first in first out replacement algorithm. This algorithm associates with each page the time when the page was brought into the memory. Okay, and when page must be replaced, then the old page is chosen. Okay, we'll see an example how this FIFO works. Consider this is the reference string given, or you can call this as a string of memory references. That means to execute a process, these are the pages that are required and the order remains same. So to complete the execution of a process, this reference string is followed. That is, first it will access page 1, then 3, followed by 3, followed by 3 again, followed by 5, followed by 6, and followed by 3. Okay, so now we'll see how this FIFO algorithm works. Initially we define the capacity, which is nothing but the frames, or you can say the size of the memory. In our example, we'll consider 3 frames here, 1, 2, 3. Okay, and we'll place this reference string or the pages into the memory, and we'll see how this FIFO works. Okay, and we'll find out when page fault happens. Okay, so now let us consider the first frames that I have considered here. Okay, so initially you can see all the frames are empty. So if this page 1 need to be considered for the execution of particular process, then that should be brought into the main memory, right? So since it is not present in the main memory, there is a page fault at this point. Let me represent that as page fault. Okay, and this reference string is placed in one frame. Okay, next page required is 3. Now we'll check whether this 3 is present in the main memory. It is not present, right? So that's why it has to be brought into the main memory, and this is written 1, 3. Okay, and next string is 0. Check, is it present in the main memory? No. So here also there is a page fault, and check, is the 0 in the main memory? No. So that's why it is also brought into the main memory, and there is a page fault. Now next string is 3. Now check, is it present in the main memory? Yes, it is present. So no page fault here. It remains as it is. Now next consider the next string 5. Is it present in the main memory? No, right? So now we have, since the memory is full, we have to replace any one of the frames here. Since we are following FIFO as replacement algorithm, we'll choose the first frame where we placed the first page. That is, here it is 1, right? Here it is 1. So this 1 is, we are going to replace it with the page 5 and rest remains as it is. So there is also page fault. Next string is 6. Now check in the main memory. Is it present in the main memory? No. So we will going to replace this with the first inserted frame. After 1, next inserted page is 3. So that's why we are going to replace this 3 with 6. Okay, that is also page fault. The next string is 3. Now check, is it present in the main memory? No, it's not. So next replace 0. After 3, 0 is inserted into the frame. That's why 3 is inserted at the place of 0. Okay. Now count how many page faults are generated here. 1, 2, 3, 4, 5, 6. So the page fault for this memory reference string, if FIFO is fault, then it is 6. I hope this is clear. Okay. Now we'll see the coding part. So first we'll see the design part. So initially what I'll do, will consider the capacity, that is the number of pages that memory can hold. Okay, that means capacity, the number of frames that we consider in our problem. Next is, let set be the current set of the pages in the memory, and then start traversing the pages, that is reference string. If set holds less pages than the capacity, then insert page into the set one by one until the size of the set reaches the capacity or all page requests are processed. Okay, simultaneously maintain the pages in the queue to perform FIFO and then increment page fault. Okay, and if that condition is false, then else condition will execute. But if current page is present in the set, then do nothing. Else remove the first page from the queue as it was the first to be entered in the memory. Okay, since FIFO we are following. Replace the first page in the queue with the current page in the string. Okay, then store current page in the queue. Then increment page fault and return that page fault. We'll see the code now. As per the syllabus, the question asked here is design, develop and implement a C or C++ Java program to implement page replacement algorithms, FIFO and LRU. Okay, we'll start with the code. As main function, we can see here main function where the pages or the reference string is given, the number of pages, the order in which pages are referred is given, and capacity is also declared here. So here it is 4 and we are calling the page fault function here. Okay, page fault. Now come to the class where, so you can see in this code I'm using hash set, linked list and queue. So to implement this, I'm going to use all this hash set, linked list and queue. See, as I said, a set is maintained, right? So to maintain that set, I'm going to use hash set here, which is advanced Java, and this FIFO is implemented with the help of queue, and this queue will be implemented in the form of linked list. That's why I'm considering all this. Let's start with the coding part. Come to the page fault function. Okay, first what we'll do, we'll define a set of type hash set. Okay, once the set is created, and it will be of size capacity that we have declared in the main function. If it is 3, s will be of size 3, and if it is 4, then s will be, the capacity of s will be 4 itself. Okay, next, as I said, queue is implemented in the form of linked list. Okay, and variable is considered, that is page fault is equal to 0, and we are going to traverse all the elements that is present in the reference string. So we have to go through all the pages that is present in the reference string. That's why the for loop is considered here. And then we'll check whether if the set can hold more pages. Okay, how do we check it? For this we are calling the size on the set, the size function on the set. Okay, the size function in hash set returns the number of elements in the hash set. Okay, so initially no elements are included in the set. Okay, so initially it will be 0. Okay, so that will be checked with the capacity. Okay, if it is lesser, we'll then check the particular reference string, that is the first reference string, is it contained in the set. If if it is not contained in the set, then add that page to the set. Okay, so if you are adding a particular page into the set, that means there is a page fault, right? So then increment the page fault. Okay, and then add that particular page into the queue as well. Fine. So next is, if the condition fails, if size is this condition, if size is lesser than capacity, if this condition fails, then else part will be executed. Here we'll check whether that particular page is contained in the set. Okay, if not, not equal, we are giving here not equal. If it is that, if the particular page is not there in the set, then find out for the linked list we are using a peek function which says to view the head of the queue without removing it, returns null if queue is empty. So peek function is called on the queue, okay, which returns the head of the queue. So whatever value that is present at the head of the queue will be assigned to val. It is one more variable considered. And then poll function is called on indexes. This poll function removes the top of the element that is present at the head of the queue. Okay, and then s dot remove of val. S refers to the set, right? So the value that is present at the variable val is removed from the set s. Okay, and then add the page which is not there in the list into the set. Okay, and then the new page we all need to add it to the queue as well, and then increment the page fault. Okay, so after this we have to return the particular page fault number. Okay, now we'll consider example and we'll go parallelly with the code. Okay, let's see the code now. So here we'll go parallelly. First we'll consider this example itself. Reference string as 1303563. Okay, initially s will be set to the size of capacity, right? So s can hold 3 elements. Okay, so that is represented in the form of set, and then according to the code page fault is 0, and then iteration starts. We'll start from the first element or the first string in the reference string. I is equal to 0. I is equal to 0 means it is 1 here, 1. So we'll check the size according to the code. Size s dot size, that means number of elements that is present in the set. So initially it is 0, right? You can see here initially it is 0. is it lesser than the capacity? Let us consider for this example capacity as 3. If this is lesser than capacity, that means 0 is lesser than capacity, then we'll check whether this particular page is in the set. Whether this particular page is in the set. Okay. So it is not present in the set, right? So then what we have to do? We have to add that page to the set. S dot add of page of I. Okay. Then that is added to the set. Okay. Then increment the page fault. According to the code, you can see here, increment the page fault. Okay. That is increment the page fault. And also we have to add that to the queue, right? So indexes dot add of pages of I. We can see in the code we have created indexes for the queue, and we are going to implement it with the help of linked list. Okay, so the same page is added to the queue as well. That is represented in the form of linked list. Okay, this is the first thing. We'll move to the next. Similarly, we'll go to the next iteration. I becomes 1. That means the second element in the reference string. Now the size of set is 1, right? Because here 1 is added in the set. Okay, size is 1. We'll check, is it lesser than 3, right? At 3 is not 3 means which one? This one. Okay, 3 is not in the set. Okay, according to the code we have to add it to the set. Okay, increment the page number and also add that page to the indexes, right? And go to the next iteration. I is equal to 2. That means the next string in the reference string. So that is 0. Now the set, in the set we have 2 elements, right? Check that with the size of, capacity. S size with the capacity. Yes, it is lesser. So this element is not there in this list. If it is not there, add it to the set. That is 130 now. Increment the page number and same should be added to the queue as well. Okay. Go to the next iteration. I is equal to 3. That means 3 in the reference string. So now the size of set is 3. Is it lesser than 3? No, it's not true. Now control will come to the else part, right? Control will come to the else part here. Okay, and we'll check whether that particular page is in the set. Now is this 3 there in the set? Yes, it is there. So since it is there, none of the code will execute under this if condition. Okay, and it will go to the next iteration. That is I is equal to 4, which means the next string in the reference string, that is 5. The size of the set is 3. Is it lesser than 3? No, it's not, right? So the control will come to this else part. Okay, and we'll check whether that particular page is in the set. So this 5 is not there in the set. So what happens? We'll find what is val, that is by calling the function peek on indexes. This will retrieve the head of the queue. Okay, and that value is placed at in the variable val. So now what is there in peek? 1 second. So in val we have this value, head, the first. This will be written by the peek function, and this will be stored in the variable val. Okay, and then once we have this, we'll call pole function is called on the indexes. That means the returned head will be removed. Okay, and again we are removing that particular s dot remove of val. in this, from the set we are going to remove that value, that is 1 here. 1 will be removed from the list as well. Okay, and we are going to insert the new reference string into the set by using the function add on the list. Okay, and then the same again we are adding it to the indexes. So for this you can see here 1 will be removed and 5 will be added to it, and for this increment page number 4. Okay, and next go to iteration, next iteration, that is I is equal to 5, which means the next string in the reference string, that is 6. Now check the size of the set. It is 3. Is it lesser than capacity? No. Come to the else part. Check is it in the set? No, it is not there. Return the head value of the queue, that is 3 now. You can see here it is 3 now, and 3 will be removed by calling the function poll on the indexes, and then the same 3 will be removed from the set as well. 3 will be removed from the set as well, and insert the new reference string, that is 6 into the set, that is 560. Okay, and the same should be added to the queue as well, where you can see 6 is added here. Before it was 305, now 3 is removed. Queue will be having 056, and page fault will be written, that is 5 here. Okay, now come to the next iteration. I is equal to 6, which means 3 in the reference string. Check the size with capacity. Is it lesser? No, it's not. Come to the else condition. 3 is not there in the set. The head value of the queue will be written, that is 0 here, and this 0 is removed from the queue and also from the set, and the new page will be inserted into the set as well as on the queue. Now the queue will have 563 as element, set will have 563 as elements. Since a newly inserted page, there is a page fault, that is 6, and the 6 will be written as number of page faults. This concludes first in first out page replacement algorithm. Thank you.